All right, perfect. I think we got a good number of people in the audience, a few more people coming in, but I think we'll get started in the interest of time. So my name is Lucas. I'm the founder of pganalyze, and today we're going to talk about optimizing slow queries with Explain to fix bad query plans. The idea behind this webinar today is that I want to teach you the most essential skills in how to tune queries. I want to share my own experience that I've collected over many years working with Postgres. And I want to do this mostly not talking about pganalyze the product, but really talking about Postgres and Explain. So if you don't use pganalyze today, that's not a problem. We're not going to show the product much today. It's really going to be focused on the core Postgres tools that we have available in any Postgres installation. Also, if you have questions, please feel free to use the Q&A functionality built into Zoom to queue up your question as we go through the materials today. And then at the end, we'll get to the questions and we do the Q&A. Depending on the time, we're roughly planning 1 hour for the webinar today, including Q&A. We might go over a few minutes if there's lots of questions. Although if there's too many questions to answer at the same time, we'll get back to you by email, essentially with a recording tomorrow, as well as the Q&A that we didn't get to today. Also, to answer that question right away, since somebody asked about the recording, so the recording will be published both on our website as well as by email. If you're registered, you'll get the recording as well, so you can share it with your team. Then one last note, in the webinar chat, Manuel from our team is going to leave a few links that are useful and related to what we're talking about. So you'll find some additional references, materials to what we kind of discussed today. Now, here are kind of the topics that we have for today. So there's 7 things I want to talk about. We'll start with talking about the iterative process of optimizing a query. So essentially, what's the general process that we would follow when we optimize a query? Then we talk about how to interpret, explain, analyze buffers specifically. And we'll talk more about what that means in a second. We'll talk about cost estimation and selectivity. Then talk about join order and parameterized index scans. We'll talk a bit about bounded sorts and how Postgres sometimes picks the wrong plan in those situations. Talk about how we can guide the Postgres planner to the right query plan. And last, we'll talk about how Postgres settings influence planning. Now, before we get started, I want to mention one more thing, which is I know today in the audience, we have a mix of people that are either, data platform engineers like SREs, or you're people that work directly on the application. And so you might not be, familiar with all the terminology here. Part of why I think it's so important for us to talk about this, not just on the database reliability side, but really across the organization, is because these skills will be useful when you collaborate with your colleagues on optimizing slow queries. And this really is a team effort. So queries are usually not solved and not optimized in isolation. Really, you need understanding of the application side of the data model and such. And so my hope today is, if you're an application engineer and you're not familiar with all these terms, that you leave here with better terminology, better vocabulary, better skills to be able to work more effectively with your colleagues. On the other hand, if you're on the database reliability team, maybe there's a few things today here that you didn't hear previously that you'll now have more understanding of. As mentioned, if you have questions, please use the Q&A feature. If you have clarification questions, I'll also come to these at the end. Now, let's talk a little bit about just the general process of how we optimize a query. So, usually, it might either start with, why is our database spending so much time, I/O time, CPU time, and such, or we might already have a particular slow query. Now, usually, when we come to this from the high level metrics, what we need is something like pganalyze or other tools that show us what queries are actively running, are actively consuming time. Now, if you have a tool like pganalyze will flag to you the specific queries that are interesting. It will show to you, if you have it enabled, the explain plan for that particular query. For today, we're, however, going to assume that you don't necessarily have that. So for today, we'll assume that you will essentially run and explain yourself using, for today's example, we'll use the text-based format. But the idea essentially is that you can use the explain statement to get the execution plan of the particular query, like the way how Postgres interpreted this query and executed this query. Now, one important thing to know about how the planner works is that the planner is essentially a fuzzy kind of thing. So the planner doesn't necessarily have, the perfect plan that it comes up with. There are many valid plans for a query, and it's not necessarily always clear which one is the best plan. This was something that Tom Lane had noted many years ago at PGCon, and it still holds true today. So really, the Postgres' planner responsibilities, right? The planner is what comes up with the execution plan, how the query should run. The planner has to find a good query plan. It has to not spend too much time or memory on finding that plan. and it has to support all the different extensible aspects of Postgres, right? So just one example, today we have a lot of PG vector type workloads, for example, that support AI embedding type workloads, and those are also planned by the same Postgres planner that didn't know about the fact that embeddings existed. And really, what's so powerful about Postgres is that you can add a vector data type without changing the core code. Now, that does mean, however, that sometimes the planner might not have to write estimations for some of these new data types or maybe for some of the new indexes. And so it's really important to run explain and to really see what did the planner think makes sense. Now, what the planner definitely doesn't do is it doesn't find all possible query plans. So it tries to discard seemingly worse plans quickly. There are some edge cases where that can be a problem. For example, when you have a lot of joins in a query, Postgres might not find the optimal plan on its own. It might also, well, it doesn't realize when expectations hold true. So, for example, sometimes there's a lot more rows being returned than what Postgres actually expected. And so Postgres does not realize that. There's no logic that says, oh, I suddenly got more data. It will unfortunately happily keep doing a really slow query for many hours in some extreme cases. And also, Postgres' planner itself does not track execution performance. So it will happily keep producing slow queries, as mentioned, which means that really the responsibility is ours to watch, what is Postgres doing? Is it choosing reasonable plans or not? Now, my general experience in how these things are done, right, is you have a slow query, and you're like, this is slow. Can I improve it? Like, what should I do? And so really the first important step is we run explain analyze. I'll show more on that in a second. We then have to form a thesis on what to change. And this comes back to the cross-functional nature of this, because oftentimes to form a thesis, you need to understand the data model. You need to understand, which indexes exist, why they exist. Can you modify the query? Like all these things is where we need to collaborate across the organization to really, understand what can be changed. Then we got to try out the change, right? Maybe that was a rewriting a query. Maybe that was, adding an index. There's a couple of things that we'll talk about later there. But the idea is that you then essentially go back to benchmarking the query again. And then if you're successful with benchmarking the query and you got it to be fast, then you want to make the change permanent, right? And so really it's this core loop that we're working on. And what I want to essentially give you today is some better ideas on which theses to try, essentially. So when you're experiencing a slow query, what can you try out? What are things worth trying based on your understanding of the planner, which we'll talk about today, as well as your understanding of the data model that you hopefully already have, essentially. And so let's talk a little bit about how we can interpret, explain, analyze buffers. And really the most important things to know about here is explain without analyze. If you just say explain in your query, that will give you the plan that the planner chose, but it won't actually give you any actual statistics. So it will essentially tell you what the planner intends, well, what the planner did and what the executor in Postgres intends to do, but it doesn't tell you whether that worked or not. Explain analyze, on the other hand, will give you the plan chosen plus the runtime statistics. So analyze is really the most important asset in our kind of testing, because we don't just see planner thought it would get 5,000 rows, but we actually see it got 1,000,000 rows, right? Like there were misestimates and whatnot. Now, one more thing that's really useful is explain analyze buffers. You write it exactly as it's here on the slide. So you essentially just put this in front of your query, you run this, and we'll give you a text output. And what explain analyze buffers will do is we'll give you IO statistics. It will tell you how much data Postgres had to load in order to execute the query. Oftentimes on production systems, our problems are more caused by either like bad query plans, or if it's a good query plan, sometimes what happens is it's not in memory, but it's in, it has to be loaded from disk, and then things are slow. And so we'll see that with the buffers option. Now, to be very clear, right, what we're talking about here is you literally go, in this case, a pSQL shell, but you can run this in basically any Postgres client. You just write explain in front of your query. What you'll get is something like this. If you write explain analyze, what you'll get is, this is the same query, just with analyze added. And so you'll see here, for example, Postgres knew in the explain that it was going to do a parallel sequential scan. But in the explain analyze, we see how many workers it actually launched, and we see how many rows it removed in that sequential scan, right? Because we're looking for a particular value here. And so a sequential scan essentially has to scan over a lot of the data. This is also a good example of where we need to start thinking about what is Postgres actually telling us here. So I'll just call this out now in this plan. What can be confusing is that you see how the parallel sequential scan at the end says loops equals 3. So that means Postgres, when it runs a parallel query, will run, in this case, 2 workers, and it will run the leader, which is the one that essentially launched the parallel query. So in total, there's 3 different processes doing a sequential scan here. So we're looping 3 times. Now, what that means also is the rows removed by filter has to be multiplied by 3 because it's the average across the workers. So really, we removed 10 million rows, not just 3.3 million. And so these are the kinds of things where it gets a bit tricky sometimes to interpret plans correctly, and really watch out when you see loop counters in a plan, because that, can get confusing fast. Now, when we have explain analyze buffers, what gets added is we have additional measurements around the number of buffers hit or pages hit. And also, if you have I/O timing enabled, it will show the I/O timings. And that's very useful here because we can understand, for example, that here in this case, 1/3 of the query essentially was I/O intensive. Note that because we have parallel query, there's some things that you need to be careful with here and how to interpret this. So sometimes when you look at I/O timings, it might make sense to turn off parallel query. Now, buffers, what does that do, right? It gives you these counts essentially that are tracked internally. One buffer is one 8 KB buffer page. So if you look at this example here, it shows us that, we had 41,000 buffers read. What that means is you have to multiply 41,000 times 8 KB to get the actual number, right? So that's actually quite a good amount of data. Now, the other thing to watch out for here with buffers, and why buffers can be quite useful, is that it tells you it gives you a sense for how many pages Postgres had to look at as compared to maybe how much data Postgres actually was looking for. So, for example, if you have a very bloated table, queries can be quite slow. Nikolai had a good example of this in a blog post a couple of years ago. But here, for example, you can see in the fast case, like both queries are essentially identical, right? They're doing an index scan, and the index scan is returning roughly the same number of rows. And really the difference here is that in one case it was very bloated, in the other case it wasn't. In the bloated case, you had an execution time of 350 milliseconds, much, much slower. In the fast case, it was 0.4 milliseconds. And the only difference here was that the pages that Postgres was looking through, they were bloated, and so it was much slower. And the way you can see that is in the buffers count, right? So if the buffers seem extremely high, then it might be caused by that rows are bloat. However, you got to be careful with one thing here. And I'll say this now because you're talking about buffers, but it's a little bit in the weeds. But if you interpret shared buffer hit counts in a query plan, really be careful if you have this inside a loop, because Postgres, unfortunately, doesn't, like, it will happily double count a buffer. So here, in this case, you see in the top, we have sequential scan shared hit 12. That essentially says Postgres, when it was doing a sequential scan, it was looking for 12 pages, 12 buffers. These were all in memory, right? So it was a cache hit essentially in the shared buffers. So it didn't have to go to disk. Now, in the other case here, the index scan has a shared hit of 1,200 blocks, 1,200 buffers. And you would think that that means that we actually loaded 1,200 independent kind of buffers, and there was actually a lot of data being loaded. But the problem is that that may not be true because we looped over this index scan 100 times. And so just be careful when you're interpreting shared hit buffers, because Postgres doesn't count distinct buffers. It really counts, if you access the same thing again. And so this is one of the tricks here to look at when you interpret buffers. But I want to say one last thing, just talking about how you want to explain effectively. And one of the challenges can be that explain analyze can have overhead. And this overhead, it's definitely varying by query plan. But one of the most important things to consider is when you're doing testing, usually what I like to do is, like when I'm interactively testing a particular query, I like to use \timing and just run the query directly and then measure essentially how long the query took compared to doing an explain analyze on it. And so here's an example where, the measurements can be quite different. So on the left side, you have for context, this table has 10 million rows, 10 million and one rows, technically. And on the left side, we can see that with \timing, if we just say, give me one row from this table, it takes 2.4 milliseconds. Now, if we run explain analyze timing off, which means, Postgres doesn't essentially do the internal accounting for how fast certain plan nodes were, surprisingly, the query is faster, and it stays fast with all the other options. Really, what this means is that we're just returning one row. The overhead is around the serialization. It's around, actually returning the data to the client. Like, the one thing to watch out for \timing is that it does include the round trip time from your client to the server. And so, it's not a perfect measurement by any way. But what this would tell you here in this case is that, clearly explain analyze itself is fast, right? So if we're looking at that, that's good. Now on the right side here is where you got to be careful. So here we're working with the full set of 10 million rows. And if you do the backslash timing, the measurement from the client, essentially, we see it takes 340 milliseconds. For context, I did run this a few times because the measurements do vary, right? So usually I say run it 3 times and take the best out of three, essentially. You might also want to take the average out of three. And so here we can see that, it was 340 milliseconds with the client-side measurement. Once I was doing explain analyze in particular, it got slower. And this is expected, right? Because Postgres has to track more information when it does these explain analyze plans. Now it did this with timing off first. That increased the, made it a little bit slower. I added buffers that made it a little bit more slower. And then really the extreme case here, and this is an exceptional case, but if you run this with timing on, and it's a count star on lots of rows, you'll actually see the query essentially get 3 times as slow in this example. This is local, so it's not usually as bad in production. But really what I'm trying to say here is if you want to make sure that you're comparing apples to apples and oranges to oranges, make sure that you actually run the query without explain as well, to really understand what the client side improvement is going to be. Now let's talk a little bit about how the planner makes its decisions, right? Like how the planner actually comes upon picking a particular plan. So ultimately, cost estimation drives the planner's behavior. It generates and rejects plans you want, and if it doesn't do that, you need to really fix the cost estimation, because ultimately the planner will pick a plan based on its cost estimation, and so the way you control this is by changing, by fixing costs. And really, as Tom said in the minimalist post a couple of years ago, is garbage in, garbage out, right? So the idea really is, if you give the planner bad data, then the planner is not going to be able to come up with a good query plan. Just to explain a little bit more what we see when we look at an explain plan. So this is not the analyzed version. This is just the explain, like the estimated version. So the cost that the planner shows us here, those are essentially arbitrary units that are mostly used for comparison purposes to other potential plans. Now, the first portion of this is called the startup cost. That's the effort it takes to get the first row from a node. And this matters a lot when you're, for example, like earlier I had an example where I was doing select star from a table, limit 1, right? And so in those cases where you have a limit, the startup cost is very important because you're just reading one row. And so you're just going to consume essentially the startup cost, but you're not going to be needing the whole cost. Because the total cost, that's essentially if you were to execute the full sequential scan on the whole table in that example. Now, the output row count, that's essentially what influences whatever consumes that node, how many rows can be expected to be resulting there. And then the width is roughly how big these rows are, right, bytes. And so here we can say the planner expects there to be 10,000 rows returned, which are roughly 53 bytes in width, essentially. But yeah, what is cost, right? Like it's not a specific unit. Really, it's the planner doing a cost-based search. And just to look in this a little bit more detail, like how does the planner actually come up with these things? So if we look at the planner source code, this is a simplified version of this, but there is a function that says cost sequential scan, and it will look at for the given table space, what is the kind of config setting that is set for the sequential page cost. And we'll multiply that by the number of pages, like the number of 8 kilobyte pages in the table. And, that's essentially the total cost. And the startup cost, is a fraction of that. Lots of details to, other costs like CPU costs and whatnot, but really, the cost of a sequential scan in a sense is very simple, right? Because it's literally saying, well, how big is the table? And what's that, magic cost constant that the planner essentially maintains or that you set as a user. And that's the cost value of the sequential scan. Now, costs of an index scan are a little bit more complicated. So this is the most important thing to note there is that it is actually dependent on which type of index you're using. There is some shared code here, but ultimately it will call the B tree, cost estimation logic, or Bren or whatever, like IVF flat, HNSW, whatever you're using. They will have different cost methods. One of the examples here, for example, in the BT cost estimate function, that's the one that's actually estimating the B-tree index scans, is that it will try to understand for the imagine you have a where condition. That where condition will have some of the parts of that are going to match the index, and so the B-tree cost estimation function is going to try to say, well, how selective is this going to be in terms of narrowing down which part of the index we're using? And so this will ultimately call the clause list selectivity function here. Um, this is one of the more important things to understand, not necessarily in the C code, source code side, but just knowing that that's what Postgres does, right? Like it will make a cost estimate, but the cost estimate is based in these selectivity estimates. And again, I'll use another Tom Lane quote here from many years ago. I think that was one of same PGCon talk. Selectivity is the hard part, right? Like this is where, you know, really things are challenging because Postgres will misestimate things. So to be clear, what the selectivity means, selectivity is essentially a number, it's a floating point value between 0.0 and 1.0. 1.0 means you're getting the whole table essentially, like it's matching everything. And 0.0001 means you're matching a very small portion of the table. Right? So essentially it says, you know, how much of the table are we looking at? It also is used to then estimate, you know, how many rows are being returned from a particular node, right? So it influences, in the case of an index scan, how much of the index do we expect to be scanning, but then also how many rows, you know, do we expect to be returned from that index scan. So, you know, here, for example, in this case, like, let's say you do a sequential scan, you have a filter statement, you're, you know, kind of multiplying the total rows in the table by the selectivity estimate for that expression, right? Like, so Postgres will try to estimate for this user ID equals 123, is this, you know, 1% of the table, 10% of the table? Like, how frequent is this user ID? And then Postgres will essentially make the row estimate. And in this case, it's just going to be the row estimate on the sequential scan. You know, one of the most common cases that I've seen for bad row estimates is when these clauses, like in your where clause, they're not actually independent. So like, for example, here we have A equals 1 and B equals 1 and C equals 1, D equals 1 and E equals 1. But imagine that you have, you know, every time A equals 1, you know that E equals 1 is automatically true because every, like, good example would be, let's suppose you have a table of employees and you have employee ID and company ID. All the, you know, employee IDs are going to have a given company ID. And so Postgres does not know that, right? And so there's the create statistics command in Postgres, also called extended statistics, which essentially instructs Postgres to collect additional information from your table to then essentially give Postgres this information about these functional dependencies, so that then usually what will happen is you will actually see row estimates go up, right? So usually what will happen is if you don't have create statistics, you'll have a very small row estimate, but then Postgres will actually get a lot more rows, versus if you do create statistics on the kind of columns involved, then you'll see a better estimate. Another example, and this is a lot more tricky, are join estimates. So join estimates, you know, like you have, in this case, you're joining two different tables. Let's suppose, for example, you know, they have one case 1,500 rows, the other case 100 rows, and you're joining them together. And, you know, of course, like there's only going to be there's going to be join filter, right? And only some of these rows are going to be essentially successfully returned. And so let's suppose Postgres, for example, assumes that it will actually only return one row here. And it does that based on, you know, similar selectivity calculations. There's, you know, bunch of logic around this. One of the things that Postgres does use here is it uses the most common value lists, which are essentially samples collected during analyze from the table. But, you know, that, like, there are definitely cases that I've seen where that is not sufficient. And so what you could do, in some cases this makes sense, there is what's called the default statistics target, and then also a statistics target per table column. And so one thing you can do is on individual columns in a table, you can say, I want more statistics, and then you run analyze, and then you get more of these most common value lists. So the idea is that, you know, this will help you essentially estimate better and get better join estimates. And this is a good example of where we gotta try something, right? So like we would essentially make that change, try it out in the table, and then run analyze. Now, I want to call out one more thing here, and we recently added this as an explicit feature into pganalyze, which is there's a particular anti-pattern around join estimates as it comes to nested loops. So nested loop in Postgres, that's essentially a way of joining two tables. And oftentimes it's an inefficient way of joining when you have a lot of rows. Postgres will choose this join type for various reasons, which we'll get about in a second. But one of the things that you should look for in a plan is when you see like this, you know, this estimate here at the bottom, we can see rows equals 1. And then we can see actual rows equals 1007. So that means that, the planner thought it's going to return one row, but it actually returned 1007 rows. And so pganalyze is able to detect these cases. Here's another example from a different plan. And then it's able to essentially suggest to you that, well, you should really look at this because here, for example, we can see that, this nested loop had a misestimate. There's actually two nested loops here. And then Postgres thought, the plan was cheap, essentially. The plan was chosen because in this case, it thought it's only going to run this aggregate function once, and it's also going to run the index only scan once. But it's actually, actually had to run it a lot more times. And that, essentially messes with your plans and oftentimes gets you more inefficient plans. Now, take a quick moment there. Let's talk a little bit about a join order. So join order and parameterized index scans are one of the most, I think, the most surprising things if you haven't looked at this part in Postgres before. And this is something you can influence and essentially experiment with. So, the like lots more Tom Lane quotes. Let's skip over this one just to not confuse you all. But essentially, the roughly, what the planner will do is it will try to say what's the cheapest path for each of the relations involved in the plan. And then it will also come up with, and we'll come back to that in a second, it will also say if this is a parameterized index scan, what is the cheapest path? And path, for context here, essentially means a plan node. And so, an example like this, we essentially have A, B, and C. So the planner comes up with these base relations that it's working with, and then has to make a decision, right? Like, for example, you could look at this plan, you could say, well, what would make sense here is for A, we're not, like there's no filter clause, right? There's no work condition on A. And so probably we should just do a sequential scan, right? Because like what else would we be filtering on? Even if something was indexed, we couldn't use it. On B, for example, suppose we have a B2 index on X, we could just, use that index scan. And on C, we could also use that same, index scan. So that's pretty straightforward. In those cases, Postgres then also has to choose what's the right join order, right? So this, in this case is still somewhat straightforward, but, imagine you have a really complex analytical query, you're joining, tens of tables. Really, this is where a lot of the, kind of like smartness or sometimes not smartness of the planner has to essentially take effect. And so, in this particular example from earlier, you have, for example, you could say, well, let's join A with B, right? Let's get the sequential scan on A, let's do the index scan on B, and let's do nested loop join, for example. And then after that's joined together, join in the C. Now, this could also be different, right? So here, for example, all we're doing is we're saying, well, do we first, join A and B, or do we first join A and C? Both are valid choices. And so one way to represent join order, and this is just, simplified syntax essentially, is to just say, which like the first table space the second table, put parentheses around it, and then space the third table in this case. And this really means, first we join A and B, and then we join the result of that with C. Now, you could go a little bit more if you want to go into more detail, like the Postgres documentation, like the internal source code documentation sometimes uses this, where it says, actually, what kind of join is it? And then also what kind of predicate it's joining on. So like, what's the join condition between those two tables? This is, really tricky. Postgres has what's called the genetic query optimizer, which it will use if you join a lot of tables. By default, that's 12. I think that's still default these days. But that like there's a lot of more logic to this. Now, this we won't talk as much about if you have a lot of joins. I think that's its own talk essentially. But just the most important things to know is the planner has to choose which scan methods to use, right? Sequential scan, index scan, on which of the indexes. It has to use the join order, and it has to choose the join methods. And so we've done some exploration here on the pganalyze site to say, for a given query plan, can we detect this, right? And so you can, right? Like there's ways to essentially run analysis on top of this to kind of come up with what's the current join order. And also, if you have auto explain, for example, you can say across the collected explain plans, what are the join orders we're seeing? Now, you can also do this, of course, when you're looking at a plan, right? Here is one of the more puzzling things about, kind of how join order influences things. So here we have an example where in the join condition, this is very typical, I would say, in the typical application query, where you're joining one table with the other table, and you're saying, in this case, t1.id equals t2.t1id. And so in this example, in order to, scan T2, it has to, first know what T1's values are, right? And so here, for example, in this explain plan, we can see that it does a hash join. Hash join essentially means they're being scanned independently. And so for T2, in this case, it just, gets all the data sequentially. And then for the other one, it is able to essentially do bitmap scan based on, the T1 field being a certain value, and then it hashes that and then it joins them together. Now, there's kind of an edge case here that's important to understand. I'll jump directly to an example of this. So if you look at that same plan again, but now we say, what else could Postgres be doing? So depending on, the statistics, selectivity, and whatnot, Postgres might instead choose to do what's called a parameterized index scan. What you see here is essentially that, it's the exact same plan, but the difference is that now instead of doing a hash join where, the two tables are independent, we do a nested loop. And so we first do the index scan on T1 to get all the T1 values essentially. And then with those, T1 IDs present, we can now index scan the T2 index with essentially substituting the right values from the first scan, right? So there's a very important ordering here. Like it can only do, it has to first get the data from T1, and then it can look at the data in T2. It couldn't do that essentially at the same time, and more importantly, it can only do it for one of the two tables, right? But this is very common in many queries, and so when you see, an index condition that doesn't have any constant in it, it references the other table, then you know that it's doing a parameterized index scan. And again, really, that's a very, different way of essentially coming up with the plan. Must be on the inner side of nested loop, right? So the join order matters. And I'll say one last thing here, which is oftentimes, you think that's a good thing, right? Because we want index scans. Then the problem you have is that the nested loops can be inefficient, right? And so when we try to come up with alternate plans to consider, sometimes it's worth trying to not have a nested loop and not have a parameterized index scan. For example, if we look back at this example here, imagine you could say, where T1 field equals this and T2 field equals this other constant value, then, Postgres wouldn't have to do a parameterized index scan. Instead, what you would see is a hash join with, an index scan here instead of that sequential scan, right? And so that's really, I think, one of the things to practice also when you're optimizing queries is essentially playing around with, can you add additional where conditions that allow you to essentially use hash joins or merge joins, because they do oftentimes perform better than nested loops. And oftentimes the reason the nested loop is picked is because the parameterized index scan is the only way to use an index. And obviously a sequential scan would be quite slow if the table is large. All right. Roughly halfway through, just for context. So making good progress here and kind of all the important concepts, I would say that, I've definitely learned over the years. So I didn't know all of this. If you asked me like 3 years ago or 4 years ago, I definitely, didn't have a good understanding of this, and I'm still learning every day. So bounded sorts. This is another common pattern that we'll see when we optimize a query. So here is an example where we select from our users table, and we're, in this case, we're searching for a particular company, and we're, ordering by a particular other field, in this case, created at, and we're saying limit 1, right? Now, what we, have here also is we have an index on the company field, and what you would, expect Postgres to do in this case is it, because the index is in the company field, you would expect it to do an index scan, get like looking at, for example, 100,000 rows, then sort these rows by that, create that column, and then limit it to 1, right? Because we just care about the top essentially result, and then return that. Now, alternatively, suppose you had an index that was company created at. One thing that Postgres can do is it can actually, not just look at all the index entries, but it can actually use the nature of the index the fact that it's sorted to limit significantly how much of the data it has to look for in the index. And so in this case, if we have this index and company created at, we can essentially use the index to get an ordered result because B trees are ordered. And so we only have to read one row and we're done, right? Usually that's a drastic difference in performance. And so if you find yourself doing a lot of these types of queries, it does pay off quite a lot to essentially experiment with different indexes. Same idea, right? Same iterative, testing, and seeing how much your queries are influenced by that. And really, the way to think about this is like, how we can describe this is essentially a bounded sort, right? So we're essentially saying we're sorting by this, but we have a limit. And so one way I would, argue essentially is, how can you get 100 times speed up on a query that does like an order by and limit is you want to make sure that that bounded sort can be pushed to the index lookup, right? So essentially like do the right index that is able to fulfill a sort order, that will essentially make the query super fast, right? Because you have a like orders of magnitude change in how much data has to be read from the index. Trade-off here, of course, is you might then over-index your database, right? So don't do this for every query, but if you have something that's really frequently used in an application, this can make sense to optimize. Now, bounded sorts can also go wrong. So unfortunately, sometimes the planner is a little bit over-optimistic on some of these things. And so, for example, suppose you have an index on B, like similar example, right? You have A equals 1, order by B, limit 1. And when, as part of Postgres estimating queries, my apologies, as part of Postgres estimating the queries, it will say, if we, use the index on B to essentially get the sort order, right? Because suppose you have just an index on B, Postgres will think, well, what if I just need to read 100 entries and then, one of these 100 entries is going to match my A equals 1 condition, and so I can terminate early. And Postgres really likes that because it really thinks that, if the selectivity of A equals 1, like if suppose, most of the table is estimated to have an A equals 1 value, then you could imagine that, for the order by B, it just needs to read the B index for a little bit and then terminate the scan once it finds the first A equals 1. That might be a lot faster than, doing an index scan first and then sorting. And so Robert Haas a couple of years ago said, this query is my arch nemesis, meaning that, this is this kind of query comes up in production situations and then Postgres picks the wrong index essentially. And so one common case where I've seen this is in especially older Ruby on Rails releases. Rails loves to do this. So if you do like something in Ruby on Rails application, like you search a user in this case for a particular email and you get the first row, then you'll see, order by user's ID ascending, limit 1. And then Postgres will choose the primary key index for the ID here instead of using the index that you have on email, for example. A couple ways to address this. So either you create a multi-column index. So that's if you can't change the queries, one of the ways to approach it is just essentially index things in a way that Postgres finds it more appealing, like the planner essentially finds it more appealing. In this case, we have both the where condition and the order by kind of covered. Another way of doing this, and we recently did a 5 minutes Postgres episode on this, is, and this you have to modify the query for this, but you can essentially add a +0 to the order by statement. So you can do order by order ID and then add the +0 at the end. And so because you added this seemingly nonsensical +0, the Postgres planner will not, choose an index and order ID even if it existed, because it will, not think that the index fulfills that expression. And instead, it would, in this case, prefer an index on shipping date, which is what we're looking for. All right. Let's talk a little bit more about, how can we guide the planner to the right plan and how can we kind of experiment with, the different plans that we might see. So really, I think the fundamental thing to do here is we want to understand why a bad plan was chosen. And we want to start that by forcing the good plan, right? So sometimes in Postgres, you might think, like we had some examples earlier, like, was doing a sequential scan, but we wanted to do a parameterized index scan or the other way around. And so oftentimes, as you're optimizing queries, you kind of form a hypothesis of what the good plan should look like. Like you might think, hey, why is it not using this index, or why is it not using this join method? Like you essentially have a theory of what Postgres should be doing. And so really the important thing to do is we want to force it to, do the right thing essentially. And so, let's suppose for a moment that there is, the situation where we have, we search for a particular object ID and the planner comes up with a good plan. And the planner might also come up with a bad plan. And so, what you want to have happen is that the good plan has a cost, right? Like those same cost units we talked about earlier. And that cost is, let's say, 250, right? Arbitrary units. But the point is it's lower than the bad plan, right? The bad plan has cost 300. In this case, the good plan has 250 as cost. Now, what in the situation where the planner, where you pass an object ID 456, and then the planner, comes up with the bad plan that you don't like? What actually happened in those cases is that, the good plan had a higher cost than the bad plan, right? So Postgres, for one reason or the other, thought that, the plan you don't want has cost 300, the plan you do want has cost 500. And so it's simple math, right? Postgres will just pick the plan with the lowest cost. And so it picked the bad plan because it had a lower cost. So one of the ways to work this off is we can test out different planner features. So there are ways to turn off, for example, sequential scans. Now, what does turning off mean? Today, this may change in future releases, but today, up until Postgres 17 including, if you do something like set enable sequential scan off, what Postgres does is it just adds a really high number to the costs for sequential scans, right? So an example here, let's suppose the sequential scan has a cost of 300, the index scan has a cost of 500. If you do set enable sec scan off, then sequential scan becomes essentially completely uninteresting to Postgres. So we'll pick the index scan. You can do this on a per connection basis, right? So to be clear, I'm not advocating for you to turn off sequential scans for your whole system because this will lead to bad plans when you don't want them. But certainly, you can do this on a per connection basis to run this and then run the explain. And what we're trying to get is we're trying to essentially understand what was the cost value that Postgres calculated for our index scan, right? Because we don't actually see that until we turn off the sequential scan. Now, when we look at an explain plan, we then want to see which part of the plan went wrong, right? Like where did Postgres go wrong? You can do some other things too. Like for example, you can, if you like, let's suppose, for example, you see Postgres not using a parameterized index scan, you could turn off merge join, turn off hash join, and the Postgres will essentially really, really prefer a nested loop. Now, one of the things that, I find most useful if I'm getting into complicated queries is using the PG hint plan extension. So PG hint plan, for context, is essentially a way to do planner hints in Postgres. Planner hints are kind of frowned upon in Postgres. And really the context is if you were to use them for production, right? If you essentially got the bad plan and you're like, well, I want the good plan, what PG hint plan lets you do is essentially lets you force the good plan. But the problem is maybe statistics change and you want Postgres to react to it, and hint plan kind of overrides all of that, decision making the planner does. And so usually I wouldn't use PG hint plan production, but I would use it to understand how does the good plan look like? What are the costs of the good plan? And so here's one more example of this, kind of example of bad and good plans. So here I have a particular plan. I'm doing a select, and then I'm essentially reading a bunch of IDs, and I just want to check if something exists. Now, Postgres here chose to do a nested loop, and it chose to first do an index-only scan to get the data. It got, I think, 23 million rows, which is a lot of rows, using an index-only scan. And then it passed those, in a nested loop. It, iterated over another index, and then essentially was able to return the data. And so the bad plan here essentially has a join order where we first get this schema column stats table, and then second we get the schema table. Now, if we turn off the memoize feature, this is a Postgres 14 feature, which oftentimes can cause performance improvements. But in this case, wasn't doing what I wanted. And so I turned off memoize by saying set enable memoize off. I ran the explain again. Note that I'm just running an explain here, so I'm not even doing analyze because at this stage, what I care about is, does Postgres change the query plan? And so it's much faster to iterate if you just do explain without the analyze. And you're going to see what Postgres is going to do and how the cost estimates are. And that's really what matters to us here as we're trying to, get Postgres to pick a different plan. As we can see here, essentially it now does it the other way around, right? So now it first gets the data from the schema tables table, then with that data does a parameterized index scan on that other table. And so really, that is what I'm looking for. Now, what I can do also, and this is where it gets, this can be a little bit, this requires iteration to write correctly, but I'll try to explain. So you see that comment at the top where it says, /* plus. So that's the syntax for PG hint plan. PG hint plan lets you essentially totally override what Postgres is doing, like the planner is doing. And so in this case, we're saying leading is for the join order. So we say the join order here should be that we first scan the SCS table, the schema column stats table, and then the schema tables table. Then also for the schema column stats table, use an index only scan on this particular index. And for the other table, use an index scan, and also turn memoize off. And the reason I care about this here is I want to understand if memoize, what's essentially what's the cost without memoize, what's the cost with memoize, and how does the bad plan look like? Because one thing the memoize node does is it modifies the costs in really odd ways. Like you see here how it sits on top of that index scan, it just makes things really funky in terms of understanding them, how they're costed. And so what I did here is I essentially forced it to do the plan. Like I wanted to know the cost essentially, right? I wanted to understand why was Postgres costing it in a certain way. And so PG implant lets me do that. And sometimes PG implant can also be used to understand, like in this case, it was a bad plan, right? But I want to understand what was that cost essentially that Postgres had calculated. And so for context, right, like the good plan here had a cost of, see if I get this right, 1.4 million. The bad plan without memoize had a cost of 14 million. And the bad plan with memoize had a cost of 970,000. So in this particular example, the memoize functionality that was added in Postgres 14 essentially had misestimated some things internally in its memoize calculations, and that caused the bad plan. Now, there are ways to influence that specifically, but I think there's some more broad things to do here. So generally speaking, if you see scan selectivity issues, right, like you see row misestimates, look at create statistics, sometimes creates like the statistics target increase, especially for join selectivity. Today, create statistics operates on a per table basis. So if you have join selectivity issues, really the only thing you can do is increase the statistics target, collect more MCV values. That's going to influence things the most, essentially. Review the cost settings. We'll talk more about that in a second. Create multi-column indexes that align with the planner's biases, right? So if you have bounded sorts and the planner is going to pick a bad index, maybe a multi-column index makes sense, or maybe add that, special +0 to the expression. Now, what we didn't talk much about today, but definitely works, is when you have a complex query where the join order doesn't make sense, or you essentially find that Postgres doesn't do the right thing, you can explicitly materialize parts of the query. So you can do with X as materialized, and then essentially Postgres is going to first execute that part of the query, and then kind of use that in a result. There are some surprising things though with these materialized scans. So on all the Postgres releases up until Postgres 16, Postgres has very limited statistics that were flowing outside of a materialized scan into the rest of the query plan. And so I would only materialize queries if it's the only way to do these things, and do watch out for misestimates when using those results. And then last but not least, if you have an application where you can add more where conditions, oftentimes it makes sense to essentially try to add more where clauses, right? This again comes back to if you know your data model and you have these extra columns, just adding more information to essentially help the planner find, for example, an index that's not parameterized index scan, but it's a regular index scan. That's really quite helpful. And this is just an older example here, but like for example, one of our own applications, I had added an additional filter condition on like additional where clause, and it improved performance significantly because it was able to successfully do the better query plan. So that said, definitely always try to give the planner more information. Don't use the planner hints as the permanent solution. They're just used to help us iterate and to help us try different things as we're exploring. And then the permanent solution really should be giving Postgres better statistics, because that is much more reliable than forcing a particular planner hint. Now, I want to close with just mentioning a little bit about Postgres settings, because oftentimes people think that, what if I just tune the Postgres configuration and then Postgres would be so much smarter? And there are, I think, two cases that I know of that, might be worth mentioning here, and I'm sure there are others. First of all, as mentioned, there's a bunch of, enable settings in the Postgres planner, and these, a lot of them, like most of them are turned on by default. And so really, the most important thing to know is as you're experimenting, you can turn off different things here to try to see what Postgres does, right? So as part of us exploring an explain plan, really try to experiment with the different planner features. For example, here at the bottom, we see enable memorize default on. Sometimes, that gets confusing, makes kind of odd choices. So maybe enable memorize off is a good kind of starting point in some cases. Also, there are two planner settings. This is Postgres 16 for context documentation that are turned off by default. And you may actually want to turn these on in some cases, potentially on a per query basis. They're specifically relating to what Postgres does when it has partitions. And I previously talked about this in a 5 Minutes of Postgres episode, but essentially the problem is that Postgres doesn't turn these partition-wise join and aggregate settings on by default because they're expensive. Like it essentially take more CPU and memory during planning time. But what we'll find, this is from a blog post that Adrian Narat did in 2021, what we can find is that, for example, partition-wise aggregate actually can significantly improve query performance. So at the top here, we see a partitioned table where it doesn't depend on a bunch of, these kind of like I think 20 different partitions, then it gets the data together and then it does a hash aggregate on top of it. If you enable partition-wise aggregate to on, it will actually do the hash aggregate before aggregating the data, meaning the amount of memory that Postgres has to use and the amount, how complex the aggregate is, it's much less. But it also has to do more work, right? Like there's more planning, more complex query plan essentially involved. And so if you have complex queries with lots of partitions, you will see, for example, in this case, performance improved from 5.2 seconds to 4.6 seconds, right? So we essentially shaved off almost a full second of runtime here just by enabling that setting on. The other thing to note, one common misconfiguration is random page cost in Postgres. So, we mentioned cost earlier. These costs are influenced by these settings, in particular sequential page cost defaulting to 1 and random page cost defaulting to 4. 4 is a very conservative value that's usually not a good choice these days. Even the Postgres documentation says you should probably use 1.1 if you have a storage of low random read cost. And so what, for example, Sharon Mukherjee found a couple, I think early this year, was an example of, running an Amazon Aurora. They, changed the random page cost setting from 4 to 1, or 1.1 rather. And they found essentially 100% improvement. And just to give you one last explain plan here, the big difference they saw essentially at the top, you can see they had a query plan where it was doing a sequential scan on table 1 because the sequential scan cost was essentially much lower than the random page cost, but the query took, 11 seconds to run. Whereas when they changed the random page cost to 1.1, they got the query at the bottom where the execution time, was 10,000 times better actually in this particular example. So quite extreme difference. And really the difference here is that Postgres then thought that it would make sense to do that index-only scan. That said, there are cases that I've seen where random page cost 1.1 actually does lead to worse plans. So be careful with just interpreting this as, let me just change this to the setting, because oftentimes plans do change unexpectedly also when, making broad strokes changes like this. So it definitely is helpful to do a little bit of, explain, analyze to test these things before applying them across the fleet. And with that, we'll close here. We'll do a few more Q&A sessions. We'll have time for a few more questions through the Q&A feature in Zoom. So please, feel free to add more questions there. I see quite a few questions already. And also, just to mention, we have a survey at the end of this. So when you close, the webinar session, you'll get a quick question that essentially says, do you want to set up a conversation with us? And so if you're interested in what pganalyze can do to help you with optimizing queries, we have both current functionality that helps with this. Builds, for example, an auto explain. There's lots of things that pganalyze does today to help you. And also we have some upcoming functionality, which we'll talk more about in the future webinar. But, just suffice to say, if you're interested to learn more what, pganalyze will do in the future there, we're happy to have a conversation and learn more about what you're, kind of experiencing in terms of challenges with Postgres. With that, let me take a sip of water and then I'll go through the questions. All right. Let's see. So what's always a question by Usman. Usman asked, how can we tell if a query cannot be optimized further? That's a very good question. So let's go back to, let me see if I can, nope, that's not what I want to do. Give me just a second. Let me pop that back up. All right, let's go back here. So we are in a situation where, let's find our slides from earlier today. All right, we are here. Okay, so the question is, how can we tell if a query cannot be optimized further, right? So we are in a situation, maybe we've, tried a few things, but then, ultimately we've not, like we want to know, should we keep trying different things? And so the answer is there is no clear way of knowing for sure that you can't optimize it further. What I would say is one of the most common cases that I've seen where people ask, my query is slow, and then people say, well, you know, this query just has to be slow, usually happens when you return a lot of data, right? So one of the things that I like to do is look at the number of rows you're actually returning to the client. Because if you're returning 10 million rows to the client, and let's suppose your table has 100,000 rows. Well, let's suppose you're turning 1 million rows to client, your table has 10 million rows. So you have a factor of 10 essentially going from the source data to the result. At best, you could optimize things so that maybe you do an index scan that will, only load 1 million rows instead of 10 million rows. But really, you have very limited opportunity to optimize. Versus, let's suppose you're returning one row. Then, there's lots of ways, like we talked about bounded sorts, for example. There's lots of ways that you could essentially get to that point where you, could more quickly get to the result. And so really, as we're working through this, right, we should look at the row counts that are returned. And if we see, that really the row count that's returned is already quite high, and that is what the application needs, that's oftentimes the situation where we don't really have that many more ways to optimize. Let's see. Marcin asked, how do you know that a query is slow? I don't mean how to check how long the query takes. How do you know that the 1 second query is the slow query? It might be the fastest query possible, taking the complexity of a particular query. I think that essentially is similar to the question that Usman asked, which is, how do we know if we can't optimize it further? I think, again, it comes back to the row estimates. There are, like, you can do like speed of light type calculations, right? Like essentially how fast is your storage, how big is your, shared memory. There's just going to be limits in how much data you can return. Sometimes what also is helpful is which applies to both these questions, is take parts of the query, right? So essentially, let's suppose you have a query that does a really complex join and a really complex aggregate, but ultimately you're returning a certain amount of data. Try to simplify the query, and if that still is slow, right? Like as you're simplifying the query, and that that's because we're returning that much data, then you do essentially know that it's more of a fundamental how much data kind of return over the network and how long does that take, versus something that's inefficient on the execution side. Sahil asked a question on what does bloated mean. So bloated really means that your table is bigger than it should be. We had a long detailed webinar on this previously on auto vacuum tuning, but essentially what it means is that your table could be smaller, but it's not essentially. And let me see. I'll probably get to 4 more questions. Let me go ahead a little bit on the questions here, and then the ones we don't get to, we'll do after the fact by email. Let me see. So I think I see a question here by Les. Les asked about how do you deal with selectivity of a column that is effectively independent, for example, user ID. Is the MCV functionality the only resource? Histograms aren't really applicable. And then these are for tables that have 10 to 100 millions of rows. And so obviously, if you collect a lot of samples, that would overflow the MCV list. And so generally, Postgres does a lot of interpolation around, selectivity of columns. And so really the most important question on these kinds of tables is, if it's like analyze takes a sample of the, like a sample of your table. And so if, you if your table looks the same across these, 10 million, 100 million rows, then usually it's not a problem, even if the MCV values, for example, only, include a subset of the user IDs. Usually the estimates do end up being somewhat reasonable. Where I've seen the most challenges be is around when, some of the table is, old, like archive type data, and some of the data is fresh data. And then Postgres, the analyze essentially picks a bad sample. And so, in those situations, default statistics target might only do so much. And sometimes, like partitioning a table might make sense, right? So I would think about, is the table uniform in its distributions? And if it isn't, then, what can we do beyond increasing default statistics target? If it's, just a single column thing, then you really, probably make a small table is the best recommendation I can do there. But yeah, it's definitely a challenge. Like I've seen these things go wrong in those kinds of tables. And let me see. So we had lots of good questions. Thank you all for asking many good questions. Let me see if I can get one here. So I think there was a question that Varun Deshpande had around what pganalyze does in this context. So does pganalyze capture the actual execution plans or estimated plans? So we didn't talk much about that today, but just for context, right? If you're interested in pganalyze or you're already using pganalyze, so pganalyze has a way of capturing query plans automatically. And so what pganalyze will do is it will either do what we call log-based explain, which is just a regular explain without the analyze, or it will integrate with the auto explain extension in Postgres. And auto explain is really the recommended way of getting execution plans automatically, right? What we do here for context is we essentially get, actually I have a slide for this if I go back here. Here's an example of this, right? So pganalyze will capture the execution plan for you. And what this will help you understand is, especially for auto explain, you will know at a particular point in time when your query was slow. Was it slow because of I/O? Was it slow because it picked a particular bad query plan and such? So pganalyze can really help you get not just the estimated plans, but the actual plans as collected by the auto explain extension in Postgres. We did talk a little bit about the overhead though of explain, analyze, and so we do have a recommended set of settings for auto explain. One of the most important things to decide is whether you want to use log timing on or off. That's a longer conversation, but there's some settings that we do recommend to essentially turn off to reduce the overhead of that. And then let me see, Kevin had a good question on who are the best folks to follow to get access to some of the best thinking around performance tuning. So that's a good question because as part of, so we do a weekly video series, 5 minutes of Postgres. If you're not familiar with that, that's on YouTube and on our blog. And as part of that weekly video series, I usually try to, find good content, who knows these things best because I want to learn myself. And so the places I look for this kind of information is there is the PG SQL performance mailing list. It doesn't have a lot of activity, but oftentimes you get really high quality answers. So if you look in the Postgres mailing list and you look, there's different mailing lists like Postgres Hackers. That's like the main internal development discussion. But then PG SQL performance, that's essentially the place where people post their performance problems and people from the community respond. And so I would it's not necessarily following people, but it's following the mailing list. I find that I often learn from somebody like Tom Lane or other folks in the community responding on slow queries on the performance mailing list and understanding their thinking of how they optimize queries. Also, if you're looking for just people, to follow, if you look back to our 5 minutes of Postgres episodes, I usually try to, specifically reference who, wrote a good blog post on something. And so there's a few episodes that we referenced today in the resources also. And so I would start there if you're looking for more folks to follow. And then I think we'll take one more, let's see, we'll take one more question and the rest of them we'll do asynchronously. Let me just see if I can, which one to take. Let's see. Let's take, yeah, that's maybe a good question. So there was a question on what are the tips and tricks to speed up insert statements? Mainly because we didn't talk much about that at all today. And oftentimes, a slow query might be an insert statement. And so the thing to know about insert statements is that, oftentimes the effects of what is slow in an insert is not necessarily the the query plan directly, but essentially the subsequent work of like the wall, has to be written and such. And so usually what I find for insert statements, the quick answer to this is, if it's a really simple insert, try to do multi-row inserts or copy if you can, right? So copy is much, much faster in terms of what Postgres does. So that's the most basic implementation there. If you do an insert on, insert into and then select star from something, you ultimately have a query plan, and you have, kind of like all the optimization techniques we talked about today do apply to a statement that, reads some data and inserts it. And so in those cases, what you could do sometimes is just pick that select statement independently, do an explain, analyze on that, and kind of optimize it this way. So it does depend a lot on the specifics of your insert statement. But yeah, I would essentially start with trying to see, are you actually bounded on the writing side of it, or are you bounded on, getting the data for the insert in the first place? All right, well, there's lots more questions, but not enough time, unfortunately, to answer all of them today. So what we'll do, just to repeat again, we'll send out tomorrow, you'll get an email if you're registered for the webinar with the recording and with answers to all the questions that we didn't get to live today. We'll take time to answer, as many as we can of those. And so you'll get your responses to these questions by tomorrow in email. Thank you again for joining. Really appreciate, so many folks joining today, and looking forward to talking more in the future. Thank you, everyone.